Hi everyone, welcome to this TriboNet seminar. And today we have an interesting topic on chocolate tribology. And the speaker is from University of Leeds. So I would give a short introduction about the speaker, and then we'll have his presentation, and then it will be followed by the questionnaires. So today's speaker we have Siavash. So he's the material scientist by training, and he completed his PhD in tribochemistry and surface fatigue of wind turbine bearings in partnership with SKF. He has over 8 years of research experience in biotribology, tribochemistry, and tribocorrosion of hard solids, that is the metallic, including solid lubricants like carbon coatings and development of soft polymeric materials, example hydrogels, and he has decimated the outcome of his research activity and invited keynotes and various talks and outreach activities. He was also awarded a fellowship and grant and has collaborated with industrial sectors like SKF and Equinor, etc. And throughout his career, so his current research topic is in the area of development and tribology of soft hydrocolloid systems. Today, we'll be delivering a topic on the which we are just initially saying it's chocolate tribology. Uh, we are so happy that you are here with us, Sia, and over to you.
Thank you. Thank you, Manoj, for fantastic introduction. I'm also happy to be here as well. Thank you for the invitation as well. So starting here, obviously, my name is, so the short of it, it's Sia, basically. I'm a researcher at the University of Leeds. At the moment, I'm working at the School of Food Science. We are looking into the mainly how we can improve food systems to make them more healthy, probably, but at the same time with a minimum kind of a compromise on the taste or textural attributes of the food system. So the title of presentation obviously is about the chocolate, but we won't. I just thought maybe it would be a good idea to also speak about what is oral tribology, kind of a general perspective, because sometimes kind of a niche area and is under development still. Obviously, I have to acknowledge the funding. So the most of the works I'm presenting on this presentation, it's funded by ERC, European Research Council. And to the next slide, hopefully it goes there. Yeah. Yeah, fantastic. So basically, I can in the area of oral tribology, tribology can be a shot in the arm for food research and industry. So traditionally, rheology, the science of viscoelasticity, viscosity of fluids, they were quite important in food systems. So people were looking into the rheology of the food system and trying to understand and link basically the rheological properties of the food to their texture and taste. So, but mainly if you are speaking on this image, basically, if the food, what we call it boli, which is basically when the food is mixed with the biological fluid in our mouth, which is saliva, we call it boli. And when it forms quite a thick film, usually rheology is dominant on that regime. But then when obviously during the oral processing, the thickness of the film, the food film, becomes thinner and thinner. That's where tribology starts to play a role and becomes more important. And why is important to have a tribology kind of analysis coupled with rheology is that rheology obviously cannot distinguish and cannot explain lots of observations with food systems. One example here is that, for example, on this graph, so if you look to the zero fat yogurt and 5% fat yogurts, we all know that so 5% fat yogurt, it tastes better. It's a smoother, it's silkier. So I would very doubt that anyone would go for a zero fat apart from being it healthy, right? But if you look to the rheology or viscosity profile of the zero fat and full fat, you get basically this graph. You see these are identical. So the difference is we find 5% fat yogurt more delicious. obviously cannot be explained with rheological observations. But coming to the tribology, that can be actually quite interestingly being distinguished. So if you look to the 0% fat in a Strawberry curve kind of a thing. So if you look into the friction versus intravenous speed, the zero fat yogurt has got significantly higher friction compared to the full fat yogurt. That's where the tribology is more important. But in general, there are 4 areas that tribology contributes to the food science. One is designing healthier colloids. So basically, scientists have been trying to link the sensory attributes to the frictional responses. Sensory attributes can be a smoothness, slipperiness, saying that these are quite subjective, but there are some empirical kind of a formula and equation for them to link these basically sensory attribute to the frictional responses. Second one is detecting food adulteration or any kind of impurities in food system as well. One good example is wine, for example. So most of you, if you're drinking wine, would experience that kind of a dryness on tongue, which is in food is called astringency. And that's quite common as well. So basically what happens in these areas is that we have got some biomolecules, these saliva films on our tongue. And in wine and also in coffee and tea, we have got these tannins, these kind of some molecular structures, phenolic structures, which are interacting with the saliva and collapse that saliva, basically makes that saliva less lubricious. That's where the dryness coming into effect. And usually one good approach to tackle that. So if you're having a wine and you're enjoying having that, you can definitely continue drinking wine. But obviously one of the good approaches to having a jelly, which is polysaccharide, or kind of yogurt or baguette or bread, basically bread or crumb of a baguette, which helps with that dryness and relieves that dryness from the tongue. The third one is basically tailoring food or improving health conditions, for example, dry mouth syndrome, which is quite common for the people who suffer from some radiotherapy treatments or disease. Basically, tribology can improve that the symptoms of that syndrome, which we will be talking about in actually further slides. The fourth one is the contributing to achieving food sustainability. So there is a quite significant amount of research going on at the moment, as you would assume, going into the plant-based food system. So we are trying to have sustainability in also food system as well, rather than having kind of a meat-based or animal source food systems. So in this presentation, we're going to cover like 3 case studies. 2 of them I'm gonna go through it very quickly just to give you an idea. But third one is going to be obviously on the chocolate. So the first one is about the dry mouth, which we talked about. So it's quite actually prevalent. So it's between like a 10 to 33% of female, they sometimes during their lifetime they would suffer from these dry mouth. We won't mention about the reason of that, but obviously that also damages our teeth system as well. So at the moment, treatments are not very effective, or at least they are not long-lasting treatments. So from our previous studies, we know that the saliva films on our tongue, it's doing that lubricity, giving that low friction based on some interaction, electrostatic interaction. So there are some biomolecules which are positively and some of them negatively charged. They are interacting and they make a self-assembly kind of a mucin system to reduce the friction on our tongue. So we try to basically do a kind of a reverse biomimetic, and we mixed a microgel of a protein and with some polysaccharides at a certain concentration, and we managed to produce a kind of a hybrid system which has got polysaccharide and protein in it. We did some investigation in terms of friction measurement, as I would assume most of you know about MTM, which is from PCS. So the most traditional way to measure the friction in food system is to using MTM with PDMS silicone-based surfaces. And you can see in this graph basically is that if the saliva is the gray dots, and our formulation is actually doing better than the real human saliva when we are mixing these protein and polysaccharide under certain conditions, which was great. But the thing is that obviously we have to be more realistic in terms of food oral tribology, because PDMS doesn't represent our tongue or mouth surfaces. We have got some bumps on our tongue, which is called fungiform or filiform. So these are called in general papillae. Recently, we developed a material which replicates the surface texture, deformability, and wettability of real human tongue, and we managed to couple it to some test kits to measure some friction data. And interestingly, our formulation was also effective when we tested these with the tongue mimic materials as well. So if you look to that formulation, it's actually surpassed the friction behavior of the real human saliva. This work is under commercialization, and we are trying to make a patent on it and basically use it as a substitute material. Second one is basically improved development of food system. So we are trying to reduce, similar to the traditional like oil lubricants, for example, in engines or wind turbines. Food system also, they have got loads of additives. So it's not only protein. They've got proteins, polysaccharide, emulsifier, loads of other things. So we are trying to reduce that number of additives, because there are also similar again to the engine oil, these interactions making the understanding of food system quite complex. So we are trying to reduce the number of additives, but at the same time improve the nutritional profile, being protein. So increasing the protein amount content of the food. So we selected a polysaccharide. Polysaccharide usually is used as a rheological modifier. So there are long chain molecules and increasing the viscosity significantly. For example, in this case, dextran, as you can see, when the concentration goes up, the viscosity jumps up significantly. When it comes to the protein system, for example, one common example is whey protein. It doesn't have much of a viscosity value, but and also when it's also mixed with the polysaccharides as well, for example, whey protein plus dextran at 11%, it doesn't add much of a viscosity value. But the good thing with the protein is that they have got kind of a surface effects, and they're reducing the boundary friction, which is helping. They are absorbing onto the tongue surfaces and reducing the friction. For example, if you compare whey to dextran. So we wanted to have obviously both the rheological properties of dextran, but at the same time having the protein. So we managed to produce some microgels of these whey proteins. And we managed to tune the properties of these microgels, so the friction behavior of that is very similar to the whey protein on its own. And if we further tune that through the processing we can do, is a complex. I don't want to go into the detail, but basically the viscosity behavior of that microgel is very similar or almost identical to the dextran at 5%. We said, okay, so that's a great news. Why not we compare our system? So putting, instead of having whey plus dextran, let's compare our whey protein plus the microgel of the whey protein. And we saw a very interesting observation. Basically, regardless of you adding dextran or whey protein microgel, viscosity behavior is identical, friction behavior is identical at low concentration of the whey, at higher concentration, at medium, basically at 5% and 11%. So basically, we managed to reduce the number of additives used by tuning the whey protein and make some microgels out of that to achieve a kind of a more nutritional food, but at the same time having that rheological and the surface properties we aim for. Third one, going to the chocolate, obviously. We recently published this paper in January and received an enormous amount of attention. So probably one of the reasons is that obviously it's chocolate. Everybody loves that. They're trying to see what's going on with the chocolate. Don't want to go into the number, but it's been really good in terms of outreach activities, and we managed to have some live interviews with loads of media and news outlets. So what is this work about is that we try to understand what is the lubrication behavior of the chocolate across two scales, because that wasn't existing. So as I mentioned, the traditional way to measure friction in food system, it was just MTM, PDMS. We thought, okay, so this is not really replicating the system. Why not we try to understand the lubrication behavior in two scales, one being the single papillae. If you remember, the papillae is those fungiforms or filiforms on our tongue surfaces, and full tongue. The full tongue, obviously using that tongue mimic material we have. And we managed to also build a custom-made kind of a tribal microscopy, which has got a fluorescent optical detector, which is looking into the surfaces, the where the contact is going on, to understand, to visualize and understand what is going on with the chocolates. The other important approach of it, which was missing also in the literature, is that what is going on across the stages of eating, because eating is quite complex. So especially coming to the chocolates, which is again a complicated material, which is a phase-changing material. We sometimes starting having chocolates with leaking. Obviously, it gradually melts, so we call it molten state. And then obviously then add mixes with the saliva, which we call it bolus or boli in the system. So we wanted actually to have these three different stages to understand what is going on at different stages. Just to mention, I'm not going again into the details, but the parameters we use in terms of the contact area and also the pressure and the speed range, we measure these lubrication behavior. They're all basically very similar or identical to the conditions, real conditions in mouth. Coming to introduction to a chocolate, so this is a confocal image of a chocolate. It's kind of a microstructure of the chocolate. So as you can see, chocolate is kind of a composite material. On this image, the brown matrix is what we call cocoa butter, and the green or orangey parts of it, or yellowish part, those are cocoa particles. So those are solid particles of the cocoa. And the black contrast or voids, or those are sugar crystals. So chocolate is composed of three mainly components: sugar, cocoa solids, and also the cocoa butter. So we tested 4 samples of the chocolates, all of them actually in being dark chocolates with a very narrow distribution. So when we are saying 70%, this means that 70% of that chocolate is made of cocoa, similar with the 99%. But interestingly, there is no kind of a linear relationship between the percentage of the cocoa and total fat content. For example, in 90%, we have got highest amount of the fat, and in the 70%, we have got lowest amount of the fat. One more thing is that we usually looking into the, so this is also another difference to the traditional tribology to the food system, is that in food systems, sometimes, for example, in chocolate, we have got solid particles that they can go into the contact. That is something we don't have much of in tribology. Obviously, we have got third body particles, can indenting the surfaces, but that's a different story. These surfaces, these particles actually going and entraining into the contacts. So those are important. The size of those particles is important. Just want to mention that the chocolates we selected, they have got identical cocoa particle the sizes in there. That's important because you can't really compare a chocolate with different size of a cocoa particle to the other chocolate with a different particle size. Those are affecting our lubrication observations. Starting with the solid leaking, as I said, basically when we start leaking a chocolate, what's going on? We try to understand that across a speed range of between 0.5 millimeter per second to 50 millimeter per second. And what we observe basically is that in general, if you look into this graph, this is a solid lubricity of the chocolate, basically rubbed against a single papillae. And as the amount of or content of the fat increases, for example, the gray one, we show a lower friction compared to the green one. The gray one compared to green one, which has got a lower amount of the fat. So this means with a higher fat for the chocolate, we saw a lower friction. Then we thought, obviously, so the saliva during eating, saliva would be secreted in our mouth. So what's going on if the saliva is wetting the chocolate? So we pipetted some droplets of the the saliva, a model saliva, into the surface of the chocolate, and wanted to see what's going on. Interestingly, the frictions coefficient for those chocolates gone up by at least 3 times. So and with some observation, with some visualization, our basically conclusion was that when we have got the papillae rubbed against a solid chocolate, we have got a fat layer forming between the surfaces, reducing the friction. But when the saliva wets the surface of the chocolate, actually we are forming an aqueous film between the surfaces, and that is where the friction going up, because the aqueous lubricant cannot achieve the same amount of lubricity, same degree of lubricity that we can get it with the fat content. Going into the second stage, I think it's a bit large in size, so it takes a bit of a time to go to that. Yeah, fantastic. All right, so obviously we mentioned that we wanted to look into the 2 different also scales, so full tongue surface and the single papillae scale. Again, interestingly, what we saw is that with a with a higher amount of fat, being gray in this case, for example, compared to the green, which has got a lower amount of fat, we saw a lower friction. And there was also some other observation, interestingly. So it's that traditional Strybeck curve, we don't see it in this case. So there might be 2 reasons. One is chocolate is very complex material on its own. Second, the tongue mimic material we have is very different to the traditional engineering materials, and it's different in terms of also roughness and the pattern as well. So they are quite large compared to the engineering roughnesses. But again, with a higher fat content, we saw lower friction. So that gives us an indication that if you're increasing the fat, and probably on the surface of it, especially to the solid lubricity as well, we can achieve a more lubricious or a better surface textures for the chocolates. That was the case also for the single papillae scale with a different mechanism, because in this case, it was much more closer to the traditional tribological system. So in the case of tongue mimic, basically our conclusion was that we form a hydrodynamic lubrication film of a fat between surfaces when we are increasing the speed. But coming to the single papillae, actually these, which I will show you later on with these tribomicroscopy videos, that these solid particles of the cocoa, which are shown in these brown spherical dots here, those are actually confined or trapped between the surfaces, and those are actually increasing the friction. So what is forming that lubricious film is these chains, which are the cocoa butter chains. So we have a kind of what we call bridging effect. So these cocoa butter chains bridging in between the solid particles, and that reducing the friction. And the reason friction is going up here is not about we're forming a thicker film, which we call it hydrodynamic. It's actually quite vice versa. So basically these chains, they cannot be remained between the surfaces, which we call it impaired bridging effect. And that there are more chances of these solid particles to be in contact between the surfaces, and hence increasing the friction. And the last one, which was about in the case of when the molten chocolate is mixed with our biological fluid, which is saliva. I'm just waiting for the slide to pop up. Yep, it's going there, I think. Just struggling to load the next slide, but should be right. So meantime, what I also explain is that obviously with the solid chocolate, we have got that cocoa butter, which is forming the lubricious layer. With the molten chocolate, we have got these the fatty layer, which is now forming a liquid fat layer, oily layer. But when the chocolate is mixed with the saliva, now becomes a more complicated again phase as well, which we call it emulsion. So basically, what happens? The fat or cocoa butter, now they make droplets inside an aqueous matrix, which we call it emulsion. So these are oil in water emulsion. This was much more tricky to make conclusions out of it, but in general, we didn't see much of a differences as a factor of fat content. So this gives us an indication that what is forming basically during the boli or the saliva mixed chocolate, fat is not important anymore. So regardless of how much of a fat you put into the chocolate, that coalescence of that oil droplets makes the surfaces lubricious. That's not important how much of a fat content we have in the chocolate, which gives us some indication to design healthier chocolates. Going into the next slide, which is a summary of what we discussed in a more kind of a lay terms, simple language is, again, I'm waiting for that to load. Yeah, so this one. So in general, in solid lubricity, when we are licking a chocolate, basically, if you compare two chocolates in general, 90% and 70%, 90% having higher fat, we see lower friction, regardless of if the saliva is also, there is a saliva layer exists between the tongue surfaces. And also in the molten stage, at both scales as well. So we can see that the higher fat content drives lower friction at molten stage, both at single papilla scale and full tongue scale. Coming to the boli stage, the friction behavior is very similar for both chocolates, regardless of fat content. This gives us an indication that basically we can design a chocolates and intelligently putting the fat layer on top of the surface, so we can achieve a lubricity in the solid lubrication, and between the solid cocoa particles, so we can have again lubrication behavior in the molten stage, but in the boli stage is not important. So in the bulk of the chocolate, we can actually have less fat. So we can basically design a kind of a gradient of solid chocolates, having more solid particles in the body of the chocolate, lower fat and higher fat on the surfaces to reduce the calorie coming from that fat chocolate. So these are some also images. So basically one interesting observation we saw as well. So this is the composite material, which is chocolate. As you can see in molten stage or solid state, looks very similar. When it becomes an emulsion, when it's mixed with the saliva, we have got these droplets, yellow droplets. So these are the oil droplets coming from the fat cocoa butter, which are dispersed into the black, which is aqueous phase. What interestingly we saw is that when we are rubbing these emulsion, we see a different structure. So we are achieving much larger droplets. So that gave us an indication of a coalescence droplet. So basically, because of that tribo shear, those oil droplets are merging, becoming bigger, getting into the contact, and forming an oily layer between the tongue and the palate and reducing the friction. And through these two links, I want to show some of our tribal microscopy visualization we saw, which I have to probably unshare and use this to share. So unshare my screen. Yeah, so this is the what we see basically. So these, the green liquid or fluid, you call it as chocolate, right? And this is the contact area. And what we see, if you can notice these small particles, a small contrast of green dots in that, those are actually trapped or confined cocoa particles. So bridging effect of the cocoa butter between these solid particles is important to avoid those solid contacts of cocoa solids with our tongue surfaces to reduce the friction. And that is why sometimes you perceive a kind of a more roughy or gritty nature of the dark chocolate, because those particles with the darker chocolates, we have got higher amount of cocoa solids, and that's becomes a bit of a gritty because they are trapped between the surfaces. And into the emulsion, so back to that. And that is what we see with the emulsion. So in this case, these red contrasts, those are oil droplets. And interestingly, in the vortex of these contacts, so when the surfaces are moving, you can see some droplets dissociating and becoming bigger, for example, in this case. So these are actually the coalescence, which was also confirmed with our confocal images. And these are getting into the contact, and still you can see a small contrast of the reddish inside the contact, which is basically confirming that the coalescence of the oil droplets and entrainment of that into the contacts provides that lubricity. And that was the end of that. I hope you enjoyed the presentation. So unshare for any question if you have got any.
Great presentation, Siavash. It's a topic that not many of us know a lot about it, tribology, and I'm just fascinated of
Thank you.
what we can actually do with chocolate. It's a completely different field.
So yeah, so one of the interesting thing with the especially chocolate is that one is it is a phase change material, which we don't usually have it. So we have oil, for example, mostly in engine oils or bearings or gearboxes. We don't have much of it. So obviously, we have got grease, which is bleeding some oil, but it's not really phase change. But with chocolate, phase change is important. The second one is the solid particles. Again, we have third body wear particles, but it's not comparable to what we see in these chocolates. So we have got 70% loads of cocoa particles, which are actually not spherical most of the time. So they have got very sharp, they have got sharp edges. And if they are becoming into the contact, they are making that gritty nature of the dark chocolates. So didn't want to go also into the detail as well. So there are some indications that those traditional stripes might not be completely valid or might not be able to completely explain what's going on with the these kind of complex materials, both phase changing and also particle containing materials.
Yeah.
One quick, okay, all right.
I have a question.
Okay, please go on.
Yeah. Oh, okay. So my question is on the visualizing and exploring the microscopy and then understanding the chocolate tribology then. So did you have any standards for that? Like, since this is a new work which you have done, so did you, compare your results with any standards in understanding the visualization? And then the second is on the temperature control tests. Did you do any temperature controlled tribology tests for this?
They are, yes. All of the tongue mimic scales, all of them are done at 37 degrees because that's what we assume the oral environment temperature is. And the first question in terms of a standard, what do you mean exactly the standard?
So whenever we compare the results of a tribology, so we do refer some literature and see these are the already performed tests, and then we understand our test and then compare, and then we see what is the difference in the coefficient of friction and things. So since this chocolate tribology, since you have developed the like the tongue like material, and then you're testing the chocolate over that and then sliding. So how do you determine this is a coefficient of friction of that? So how do you say that your results are right?
We are not actually relying on the friction coefficient as a value. As you know, friction coefficient is a system value. So if you change those materials to something else, then the friction would change. We are mostly looking into the comparison and understanding the mechanism, what is going on. And in terms of comparison to the previous literature, so as far as I know, there are some works on in terms of visualization by Imperial who looked into the cocoa, which is similar. So in cocoa, sorry. So in cocoa as well, in coke, so basically we have got some carbonated, some gases, which are so basically based on Imperial Tom published that paper showing that it's going in between the surfaces and making kind of a starvation. So particles showing similar effect as well. So if you have got particles, we have kind of a starvation of film between the surfaces. So that is something we can compare. And previously, with traditional PDMS MTM materials, Jason Stocks, Professor Stocks in Australia, they did also fantastic works as well, and they showed as well the higher, the gritty nature of the dark chocolates can be linked to the higher degree of cocoa particle concentration. Yeah.
I think, Savi, you should unmute.
Okay, yeah. You know me well by now. And you got a question from Aider. Well, please
Yes.
unmute yourself and talk. Yeah.
I'm sorry, several times I was kicked out today, but I'm wondering, can you also study, so you study the tribology of wines, but can you do similar studies on whiskeys or cognacs or all this hard stuff?
Yeah, that's
well?
Yeah, that goes very strong drinks then.
Yeah. Yeah.
I mean, there is definitely a scope for it as well, yes. But the main reason we did some work in our group, not myself, but my line manager and some of my colleagues as well. They did some studies on wine as well, showing that this interaction is actually reducing the increasing friction coefficient or reducing the lubricity of mucins. The main reason is that usually with wine or coffee, we have got astringency. As far as I know, there are not much of a reports on astringency for whiskey or spirits like vodka or whatever. But there might be some scope for it, which obviously needs funding. And if you have got some funding, you would love to do that. But the next plan is obviously to look more into the cheese, soft cheese, for example, Philadelphia cheese, the more kind of a fatty nature of the system, solid fats, basically. That's part of the plan.
Okay, are you
That's nice
satisfied?
as well. Yes, that's nice as well. I also eat that cheese, so.
My question.
Thank you.
Sorry.
Thank you, Siavash.
Thank you.
There's a question from my side actually, because yeah, okay. So if someone else wants to ask a question, please let me know and we will unmute you, or just write it down in the chat. From my side, is that I've always have problems when it comes to food tribology, is to relate these tribological properties, or let's say rheological properties, to actually if the chocolate is good or it's bad, or people like it more or less. Of course, we are all different, but are there some common properties that a good chocolate has? For example, if I take 5 chocolates from the supermarket, I go to the SRV and I say, hey, these have higher friction coefficient. Will that say that this is a better chocolate? Or, you know,
great
how
question.
to connect to, yeah.
Yeah, so coming to the food system, they are very complex. One of the things is that, as you mentioned already, the perception in oral perception of food system, they are very subjective. Like, as you mentioned, somebody would like dark chocolate, somebody would hate it. So even you can't say it is because of the grittiness. Some of them doesn't like the bitter nature of that. That is what I wanted to try to get into. So we are mostly looking into the texture, which can be linked to the lubrication behavior. What with eating and what we perceive as a tasty food or delicious food is not only texture, it's not only lubrication. It has got we have got taste buds, which is a chemical neuron system, which are basically perceiving, for example, sugar some chemical interaction going on, which contributes to how we perceive the taste. Apart from that, retronasal characteristics of the food system is important. So a smell, or for example, if you enjoy crisps, when it fractures, that cracky nature of it, it contributes to how we would we like that food or not. We have to try to narrow it down, understanding it step by step. So obviously one approach can be somebody can put some of the sensor, like chemical or neural sensors into these tongue materials, so we can embed or integrate it with the taste of it as well. But it's quite difficult. Even if we do that, then we can't really look into the fracture nature of the food, or which is cracking, or also the nasal or the smell of that as well. So all of them are contributing. We can't really say that if this product, if we have got lower friction, gonna have a better market. And that's why in biggest manufacturing food industries, they usually have taste sensory trial panels. So loads of people, different backgrounds, different, like even some of them has got some health conditions. They are sitting and tasting. For an ice cream, for example, Häagen-Dazs, there are loads of people are staying there and tasting before a product can be launched into the market.
That's super interesting. I will look for vacancies at Häagen-Dazs. Okay, so I understand from your reply that there's not really a straight correlation between physical properties and that's why the goodness or like it's really subjective to the person. Okay, clear. Oh, we got the questions from Is it pretty long? Maybe we can try to mute you. Would that be okay for you? If you cannot reply, I'll try to do that. Find you. Please feel free to unmute you and ask the question directly.
Okay, he says he has issues with mic. Yeah.
Okay, so I'm gonna read it for you, Siavash. Otherwise, you have it in the chat. I don't know if you're looking in the chat.
Yeah.
Okay.
So
okay, could you read it first, and then
I think Mubashir is quite right. So there are so at the moment that previously some people use some tapes to mimic the roughness of the tongue. They are good, really good jobs. They don't replicate exactly what's going on with the tongue, because tongues, we have got different types of papillae, fungiforms, filiforms, circumvocal papillae, which have got different shapes, different sizes. People to people also changes as well. One of the other problems with those tapes is that they have got a homogeneous kind of a distribution, which is not the case with tongue. So in tongue, we have got more kind of a random distribution. So we try to replicate those as well. So it's more realistic material to tongue than those tapes. Hope that answers the question. And regarding the size of the ball and pin, exactly. So as I said, to replicate the papillae, single papillae scale, we used a pin which would have the same contact area if a tongue is compressed against palate at a certain contact pressure. The contact area is the same, similar, or let's put it in this way.
Cool. Well, he's very thankful for your reply. So if there are not more questions, I think that because you see that from
Do we have any other questions?
Thank you, Vanessa.
We don't have any other questions in the chat. Still.
Okay, so I think that with that we can close the lecture of this month.
Yeah.
To thank a lot Siavash, I'm going to say it wrong, Soltanahmadi for the meeting lecture. It's super interesting. my personal opinion,
Thank you.
you're in a really complex field.
It's
Yeah.
my pleasure. Thank you very much for having me. It was interesting, obviously, to catch up with you guys. Hope at least, I mean, I was able to add something to the to our general knowledge, basically, on that.
Yes,
That's
it
for
was
sure.
very interesting. Yeah, yeah. Thank you so much for accepting our invitation and
My
being here.
pleasure.
So for the audience, I think we will have the recording of this seminar on our website, so you can watch it if you have any doubts, and then you can also contact Siavash if you have if you want to collaborate or do any kind of other research on this. So yeah, that's it, and thank you so much for joining this webinar. Yeah, see you guys.
Thank you.
Thank you.
Have a nice day, guys, and weekend. Thank you very
Have a
much.
good Friday.
Bye-bye.
Bye.
Thank you.
Bye.
Thank you, Siavash.
Bye.
Bye-bye.
Thank you. Bye.